Hello, welcome to Computational Methods with Python. In this course, we will be using Python, so you will need to know Python to follow this course, especially the practical part. Usually, we'll introduce the numerical method first, and then we implemented it in Python. So let's start. What are computational methods? Well, computational methods is a numerical techniques by which mathematical problems are formulated so that they can be solved with arithmetic operations. I took this definition from this textbook here. So what does this mean? So reformulating the problems so that they are solved with arithmetic operations like addition, subtraction. An example in this case may be converting the differentiation to subtraction and converting integration to addition. So why this useful? Let's give an example. Here, there's the first example. I'm trying to solve an equation that's very easy to solve, right? So there's no need for numerical methods here. I will use the pen. So this is the first equation I'm trying to solve. I'm saying that this is very easy to solve, which is true. You don't need any numerical methods here. Also, this integration is very easy to solve. No need for computational methods. And this differential equation as well. Okay, so for these three examples, analytical solution exists. So no need for numerical methods. But what you do in this case? Well, this equation is really hard to solve analytically. And you will have to come up with another method, as well as this integration and this numerical or differential equation. Okay, so let's think about an approach to solve these three problems. So this 1, 2, 3. Let's think an approach to do this. Well, I know that the root is the intersection between the function and the x-axis. So this is the root here. So I can try to find a computer algorithm that finds the root by trying to find the intersection between the function and the x-axis. For the integration, I can try to find the area under the curve, which is the definition of the integration, right? So if I can calculate the area under the curve, I can integrate without having to do this analytically. And for the differential equation, I can also use the difference equation instead of the differential equation, and we'll get to this as an example today. Okay, so the idea is to write a computer algorithm to solve the problem. What is the computer algorithm? Computer algorithm is a set of instructions that allows you to solve the problem numerically. So usually implemented in computer, of course, because it will require many iterations. So the things that you cannot do in your mind or in a piece of paper. So let's give an example for this. Let's write an algorithm that solves the quadratic equation. Okay, so we know that the solution for the quadratic equation is given like this. So x equal minus b plus or minus square root of b squared minus 4ac over 2a. So there is nothing really numerical solution here, but we try to, I'm trying to explain the concept of algorithm. So our objective is to write an algorithm in Python to solve this equation. Well, this is a pretty easy example, but it's also informative, so I will follow this example. So things you have to note here that this value of the square root might be a problematic, because if then 4ac is greater than b squared, then you will have a complex number. So your algorithm should be able to deal with this situation. So in the algorithm, you will need to input a, b, and c, and then calculate d. If d is greater than 0, fine, then you have x1 and x2. If d equal to 0, then this part is 0, right? So x1 and x2 are equal. And then if this part is less than zero, then you will have a complex number. In order to do this in Python, I have the implementation here. You can try it. I also try to upload the code on Git, and I put the Git URL in the description of the video. But anyway, you can also try to write it yourself and implement it. So I'm defining a function called root. Okay, so if you're not very familiar with Python, try to follow this explanation here. So D is just b squared minus 4ac. So this is basically this step here. And then I check if d is greater than 0, fine, then I have d1, x1 and x2, and this is what do we have. What we change here is only the sign. So I change plus to minus. Okay. So, and then if d is equal to 0, else if here, I know that the x1 and x2 are equal, and this is the value here. And then else here, I have a complex number, and I solve this by, I solve this numerically by multiplying the d by -1 just to avoid getting error when you do the square root. Because if you put the a negative number under the square root, you will have a problem because d is negative. So when I multiply negative by negative, I get positive. And then I return x1 and x2. And if you can also try to pass 3, 1, minus 2 and see what numbers you get when you implement this in Python. Okay, I can show you this in the notebook later. Okay, so another example, a real example now on numerical methods and how to solve Newton's equation. Newton equations of motion. So think about object falling from the sky. So the mg, or the force, the gravitational force, is pushing the object down, and the air resistance is pushing the object up. So if I want to write the equation of motion, the acceleration, which is dv dt, equal the summation of the forces. So you have mg and negative the c minus v, which is c is a constant. So this is expressing the air resistance here. So the faster the object, the more air resistance. Okay. So at the end, the total force is mg minus cv, and then you divide by the mass. Okay. So this is a differential equation I'm trying to solve. Well, although this is having an analytical solution like this, we will assume that we don't know the analytical solution. So we will try to solve this numerically. Well, we know that also that if you plot the solution, it will be something like this. Okay, so as I mentioned, we want to solve this numerically. So this is differentiation, and the definition of the differentiation is the difference between v at t plus 1 minus v at t over the delta t. But for the actual differentiation, with no approximation, the delta t goes to 0. So with the limit goes to 0. Okay. So we can use this definition to solve this problem numerically. But in this case, delta t will not go to 0. That's why it's an approximation. Okay. So if I can rewrite this equation again here with the difference equation, and instead of differentiation, I use the difference. So I substituted this term with this term here. Okay. After that, I converted the differentiation to a subtraction. So to an arithmetic operation, as we discussed before, that the definition of the computational method is to convert these type of problems to arithmetic operations. So after that, it's very easy to solve, right? So v of t plus 1 equal v of t plus this term, which is also including v of t and the delta t. So this is the delta t here. Well, I think this is easy, but to solve this, you need a computer because you need to do iteration. You start at t equals 0, and then you go to t equal 1, to t equal 2. This is if your dt equal to 1. If the dt is maybe 0.1, then you would start at t equal to 0, and then the next iteration is t equal to 0.1. The second iteration is t equal to 0.2, and so on. Okay, so let's do this in Python. I made a function called vt, which is just returning the speed or the velocity. You pass to it dt, the time, the time step, or the delta of time, and you pass the time of the differentiation, or the time of the integration, how long you want to process this equation. So here we do it till 30, for example. Okay, so I make some definitions here. Initial velocity is 0 because this is a free fall. The mass I put it 68. I know that I put it in the slide 65. You can change this. C is I put 12.5 and G is 9.8. So all this is just defining numbers. And then I have an array to put the value of the time, and another array to put the value of velocity, and a third array to put the value of the analytical solution to compare with, because it's important to understand the error. So we'll discuss the error as well next time. Okay, and the initial time is 0. So I have initial time 0, initial velocity 0. This is a free fall. And then the number of iterations equal to the time divided by the dt. So time divided by time steps return to you the number of iterations in. Okay, so I do a for loop here, starting from 0 till the number of iteration. Each time I increase the time by dt. Okay, this is what I do here. And then I calculate the velocity based on this formula. So actually, this formula is exactly this one here. Okay, so this is the initial velocity, and this is the velocity on the next step, and this term is just this term here. Okay, and I put the time in the array, the time array, and I put the velocity in the velocity array, and I calculate the analytical solution, the exact solution, and I put it in the array of the exact solution, and then I set for the next iteration v initial to the current v. This means that in the next iteration, your initial velocity is obtained from the previous iteration. Okay, and then I return t, vt, and v analytical solution. Here, this code is just for plotting. Okay, I call the function by taking vt equal to by passing to vt time step of 3 seconds, and I do this for 30 seconds. So this is 30 seconds here. And if you do the plot, you will see that there's some difference between the approximation and the exact solution, this difference. Okay, it gets much better if you change the time step from 3 to 0.3. And makes sense, right? Because the definition of the differentiation is that the dt goes to 0. So the smaller the dt, the more accurate the solution. Okay, so this was a quick introduction to numerical methods, and next time we will discuss the error analysis, and I will put the code for you on GitHub. Good luck, and thank you.